In the last video, we looked at the general form of a tan function, which was a tan theta plus q. And we saw that q represented our vertical shift. When we had a q greater than 0, we would shift our graph upwards, such as the case in this green graph. If we had a q less than 0, such as the case with this orange graph, we would shift our curve downwards. And so we could shift each of these key points at these key angles by the same amount of units as q to easily find where our new points would be on the Cartesian plane. And in this lesson, we're going to look at the effect of A. So we saw that with the effect of Q, all we're doing is shifting upwards or downwards, but we were not changing the shape of our graph. Our graph's shape remained the same in each of these cases. It was only shifted upwards or downwards. And in the case of A, we're going to see that we can affect the shape of our graph to make it either thinner or wider. Now let's take a second to look at the effect of A on the shape of this graph. So we know that our standard form is going to be A tan theta plus Q. We've just seen that our Q was our vertical shift. Now let's take a second to focus on A and what A is going to do to this graph. So in looking at the effect of A, let's start out by trying two different examples where we have different values for A. In our first example, let's say we had an A value of 2. So our A value is 2. We're going to have 2 tan theta. And in these examples, we are ignoring the effect of Q. So we're going to envision that we have a Q of 0. So our function is f of theta is equal to 2 tan theta. So how is this graph going to change? Well, if we use the same logic that we used with Q and see how we're going to go from these standard points in our regular tan graph to new points with the effect of A, we can easily conceptualize this. So we know that over here at 0 degrees, tan of 0 degrees is going to be 0. And 2 times 0 is still 0. So our point here is going to remain at 0. Over here at 45 degrees, tan of 45 degrees is equal to 1. And 2 times 1 is 2. So our point is going to be over here. Instead of at 1, we're going to have our point at 2. We're still going to have our vertical asymptote at 90. Over here at 135 degrees, tan of 135 degrees is negative 1. 2 times negative 1 is negative 2. So we're going to have our point at negative 2 instead of negative 1. Over here, we have tan of 180 at 0. What is 2 times 0? That is still going to be 0. So our 0 stays the same. Over here, we have tan of 225 as 1. And 2 times 1 is 2. So we're going to have our point at 2. And here we're going to see the exact same thing. So where we had values of negative 1, we're now going to have values of negative 2. And where we had values of 0, we're still going to be at 0 because 2 times 0 is still 0. So now when we look at our new graph, our green graph over here, we can see that our graph has steepened a little bit. It's become thinner, and it's easier to see in this entire period between 90 and 270. We can see that our purple graph was more flattened than our green graph, and that's because at these key points, our zeros are always going to remain 0, but our points that were either at 1 or negative 1 are now going to be whatever our A value is multiplied by 1 or negative 1. So where we had negative 1s, we have negative 2s. Where we had 1s, we have 2s. So we can see that those points of inflection in our graph have become bigger. And so our graph steepens out more. So if we looked at our regular tan graph as a shape like this, a tan graph in which we have very high A values is going to look more like this. It's going to be a steeper graph. So the effect of increasing A is just going to be to thin out the graph more. The higher our A is, we're going to go from a more flat graph to a thinner graph. Now let's see what we would get if we had an A value of 1/2. So we had 1/2 tan theta. So using the same logic that we used with 2 tan theta, if we have 1/2 tan theta, we know that wherever we had 0 is going to remain 0 because anything times 0 is still 0. So over here, we're still going to be 0. Over here, we're still going to be 0. And over here, we're still going to be 0. What's going to change is our points that were either at 1 or negative 1. So wherever our point was 1, what is 1/2 times 1? That is 1/2. So wherever we had values of 1, we're now going to have values of 1/2. So here we had a value of 1 before, now we're going to have a value of 1/2. Over here, we had a value of -1, and -1 times 1/2 is -1/2. So wherever we had values of -1, we're now going to have values of -1/2. So that's going to be -1/2 over there. Here, we remember we still have 0. Here we had a value of 1. Now we're going to have a value of +1/2. Here we had a value of -1, so we're going to be at -1/2. And here we're still at 0. And if we now draw out our graphs using those dots, here we can see that with our orange graph, we have made the graph more flat. So instead of being thinner like our green graph, we have increased the flattening shape of our orange graph. So it's more flat than our purple original graph was. So if our regular tan graph had a shape like this, smaller values for A is going to make our graph become flatter and flatter. So it's going to look more like this instead of something like this. So when our values of A are decreasing, we're going to have a flatter looking graph. And when our A values are increasing, we have a thinner, steeper looking graph. So we can see that our values of A are going to change the shape of our graph to either make it thinner and steeper or flatter and wider, with higher A values making our graph thinner and steeper, and lower A values making our graph flatter and wider. Now you might be wondering, what happens if you have a negative A value? We haven't seen that yet. So what happens if, let's say you had the function f of theta is equal to negative tan theta? What happens in this case when we have a negative A? So we know that at 0 degrees, tan of 0 degrees is 0, and -0 is still going to be 0. So our 0 points are going to stay the same. We can just put in that our 0 points will stay 0. Now what about our points where we had values of 1? Negative times 1 is going to be -1. So our points that had values of 1 are now going to become -1. Over here, we had our normal tan function having a value of -1. And negative times -1 is equal to +1. So wherever we have -1 values, that's going to become +1. Wherever we had +1 values, that's going to become -1. So you might be able to guess that this graph is just going to look like a reflection of the tan graph. If we join these dots together that we've drawn, we're going to see here in blue we have our negative tan theta graph. And we can see that it's just a reflection of our regular tan theta graph. So it kind of makes this X shape with our normal tan graph. So here in purple we have our regular tan theta graph. And in blue we have our negative tan theta graph. Instead of the graph going up to the right like this, it's going to be going down to the right like that. So this is what we get if we have a positive A, and if we have a negative A, it's just going to be flipped. Instead of going up to the right, it's going to go down to the right. So this is if we have a positive A, and this is if we have a negative A.